So hello everybody, my name is Ahad Qureshi and I welcome all of you to this beautiful session in physics. So students, in today's class we're gonna see a little concept from center of mass. So let's start with a thought experiment, okay? I'm telling you, let's imagine I have a block of mass m and I've placed this block on a smooth surface and I'm attaching a spring to this block. Let's say the spring is having a spring constant equals to k. Students, the whole assembly I am attaching with a rigid support. Okay. Now if I say, students, I'm giving this block a speed v in the left side, what would happen? So all of you would say, Sergi, it's okay, the kinetic energy of this block will get converted into the potential energy, and you'll write exactly the same thing. The kinetic energy of the block is getting converted into the potential energy of the spring. Okay, sir, till this point things are going perfectly all right, so far so good. Now students, I want to make a change to this assembly. What I'm doing now is I'm actually replacing this rigid support with one more identical mass m. Now if I ask you what would happen in this scenario, so you might say, sir, the block in the right side is moving towards the left with some speed. That means the spring will start compressing, and as the spring is getting compressed, it will apply a restoring force outside. That means the left block will also start moving towards the left instantaneously. Sergi, perfectly alright, we are understanding the situation. The spring was initially in a natural length. As I give the speed to the right block will start moving towards the left. The spring will start compressing. So the spring will compress, and there will come a time, students, at which the spring will have the maximum compression. At this maximum compression, both the blocks will be moving towards the left with the same speed. Can I say that? Agreeing, students? Perfect. All right. So now the question is that I have to find the maximum elongation in the spring. All right, sir. With that being said, we will try to attempt this question. So first of all, sir, I think I should go with the conservation of momentum. So absolutely, Sergi. So that means the final speed of the blocks will be having same speeds. So I'm naming that speed to be v naught, and I can apply the initial momentum equals to the final momentum, right, students? So I can simply say that m times v is equals to initial momentum is equals to the final momentum of the system, and from this equation I can simply get the value of v naught is equals to v by 2. Remember, students, this v naught is the common speed with which both of the blocks are moving at the maximum compression of the spring. I hope you're getting till this point, right? So now what I have to do, Sergi, is initially the block in the right was having kinetic energy. The two blocks at maximum compression are also having kinetic energy. So that means the difference between their kinetic energy has been lost in the restoring force in the spring. That means the potential energy in the spring, right? So all I can say you is that, so basically I have to take the change in the kinetic energy and I have to equate it with half times of k times of x squared. So basically you have to take kinetic energy difference and equate that with half times k times of x squared. So I'm just writing initial kinetic energy is equals to half times m times v squared minus the initial final kinetic energy of each of the blocks. So it's going to be half times of m times of v naught square. V naught square is nothing but v square divided by 4, and since there are two blocks, so I'm just multiplying the whole expression by 2. I'll be left with 1 by 4 times of m times of v square again in this scenario as well. So it's just gonna be equals to half times of k times of x squared. So students, from this result we can simply say that the maximum compression in the spring is going to be v times of under root of m upon 2k. So this is the maximum compression, Sergi, when the blocks were moving together. All right, perfect, students, no problem at all. But my mood suddenly changed and I said that no, I don't want to start this experiment from the initial point. What I'm telling to you is basically I want to look at a general point. What do you mean by general point, Sergi? So you said that the blocks in the right side will move towards the left side. There will be the compression in the spring, compress, maximum compression, the speeds will be same. What after the maximum compression, students? What after the maximum compression? Can I say that the spring will try to restore itself? That means the spring will apply the force in the opposite direction, in the outward directions, right? So can I say for the left block, imagine for the left block itself, Initially at t is equals to 0, the speed of the left block was 0. Right at the same point, as soon as I applied the impulse on the right block, the left block started moving towards the left as well. At the maximum compression, the speed of the left block was v by 2. As the spring is restoring itself, the spring is applying the force on the left block in the left direction, students. So can I say that the speed of the left block is just going to increase? And the speed of the right block, you might say it is decreasing, right? So I want a general scenario. So let's say I'm taking completely general cases. I'm also replacing the masses to be m1 and m2. So let's just take a perfectly general scenario in which I have two different masses, m1 and another mass is m2. The spring constant again in this scenario is going to be k. So what's the question, Sergi? So question is that, Sergi, I have to find the elongation or the compression, whatever is there in the spring, at the instances where the speed of this m1 was v1 and the speed of this m2 was v2. So Sergi, what are you observing these speeds with respect to? I hope you're getting what I'm telling to you. So basically I'm trying to say you that the whole scenario would become much more simplified if I start observing the things from the center of mass point of view. Perfect. So Sergi, for that we will be needing the speed of the center of mass, right? So how would we be calculating that? So I'll simply write velocity of center of mass. It's gonna be m1 times of v1 bar plus m2 times of v2 bar divided by m1 plus m2. So since, students, it's a general scenario, listen to me very carefully. I told you that the initial scenario of this whole setup was something like this. So I had a mass m1. Okay, I was having a spring between them and I had a mass m2. Let's say initially I gave a speed v to the mass m2, and the final situation at which I am interested is that mass m1 is moving towards the left, mass m2 is moving towards the right. Now I want to calculate the elongation or the compression, whatever this spring is having. Perfect, Sergi. We will try to attempt that. Okay, so what should I do? What should I do, students? What should I do now? Exactly, I think I should apply the energy conservation rule. But with respect to what, Sergi? With respect to the center of mass of the whole assembly. Perfect, students. So first of all, I just have to calculate the total kinetic energy of the blocks with respect to the center of mass at this instant, students. Okay, at this instant. So I'm just gonna write half times of m1 times of this speed of this mass m1 with respect to the center of mass. Listen, students. So let's say this is the center of mass of the assembly. Imaginary point I'm telling you. Velocity of the center of mass is going to be at the left because I initially gave the impulse to the left. So I'm telling you that the relative kinetic energy of this m1 with respect to the center of mass, and I'm naming it as k1. For m2, and I'm naming the relative kinetic energy of m2 with respect to center of mass, and I'm naming it as k2. So Sergi, at any instance, if I talk about the total kinetic energy, it's going to be k1 plus k2. What about the potential energy, sir? The potential energy at any time is going to be half k times of x squared. So now, students, I just have to calculate the values of k1 and k2. Let's substitute the values. So the value of k1 is going to be half times of m1 times of relative velocity of m1 with respect to the center of mass. So I think I should simply write v1 bar minus velocity of center of mass. So that's just gonna be m1 v1 bar plus m2 v2 bar divided by m1 plus m2 raised to the power 2. So this is the kinetic energy of block 1 with respect to the center of mass. So you simplify, students, I'll simply get the value of that is equals to half m1 times of, simply you're getting m2, yeah, tell me, m2 v1 bar minus v2 bar divided by m1 plus m2 raised to the power 2. So we're just simplifying that, half times of m1 times of m2 square times of, students, see this v1 minus v2 terminology. v1 is the speed of the left block in the left side, v2 is the speed of the right block in the right side. So you can simply imagine v1 bar minus v2 bar is nothing but the relative velocity between the blocks. So I'm simply naming it as vr bar squared divided by, I'm simply writing m1 plus m2 raised to the power 2. So this is the kinetic energy one of the block with respect to the center of mass. Students, the same process I have to do with the second block as well. Since there is a symmetry, I can simply write kinetic energy K2 is going to be half times of m2 times of m1 square times simply again relative velocity whole square divided by m1 plus m2 raised to the power 2. Now what I have to do, students, is I basically have to take the addition of both of the kinetic energies. So now the total kinetic energy K1 plus K2 is going to get simplified in such a way, half times of m1 m2 square divided by m1 plus m2, sorry, so it's going to be m1 plus m2 whole square times of relative velocity Vr square, plus it's also equals to half times of m1 squared m2 times of relative velocity square divided by simply m1 plus raised to the power 2. So students, I just want to simplify this whole expression. So it's just going to come out as half times of, if I take m1 m2 common, and at the same time I'm also taking m1 plus m2 whole square also common, I'll be left with m1 plus m2 into, I'm also taking Vr square as common. So that is the whole expression. So I'll simplify that. This m1 plus m2 and this square will get cancelled, students. So I'll simply have half times of m1 m2 divided by m1 plus m2 times of relative velocity whole square. So students, this is the expression. Now I want you to imagine this m1 m2 divided by m1 plus m2. We call it reduced mass, right? Absolutely. So I can simply say at any instant the kinetic energies of the block are having half times of mu times of v relative squared, where mu is the reduced mass. And what about the potential energy, Sergi? The potential energy at any instance is going to be half kx squared. So half kx squared, where x is simply elongation or compression, whatever is there. So students, this is the total energy the system is having at any random point. So if I talk about total energy, it's going to be kinetic energy plus potential energy. So simply a half times of mu times of relative velocity at any instance plus half times of k times of x squared. Sergi, all good, all well, I understood till this point. Now what I have to do? I have to compare this energy at any instance. It is equals to the initial kinetic energy that we imparted to the blocks. So again I have to calculate the initial kinetic energy with respect to the center of mass, Sergi, right? So what is the center of mass? This is the center of mass. Okay, so this was the mass m1. I'm talking about the initial situations now. Okay, so this is the spring, this was mass m2, it was having a speed v, and this was the center of mass. Students, I'm directly writing, you can just check if you can understanding or not. I can simply say the velocity of center of mass now in this scenario is just gonna be m2v divided by m1 plus m2. Let's take the direction as well. Now if I talk about the kinetic energy, it's gonna be half times of m1 times of v1 bar minus velocity of center of mass whole square, plus again it's gonna be half times of m2 times of v2 bar divided by velocity of center of mass whole square. I hope you are getting till this point, students. So at initial instance, at t is equals to 0, the speed of the block v1 is 0. I can say that, right? So it's anyhow gonna be 0. So I'll simply write half times of m1 times of velocity of the center of mass whole square. So it's just gonna be m2v divided by m1 plus m2 whole square, plus it's just gonna be half times of m2 times of velocity of the center of mass, sorry, velocity of the second block with respect to the center of mass. So it's gonna be v minus again m2v divided by m1 plus m2. Students, it is the same expression we just encountered in the previous expression as well. So it's just gonna be half times of m1 m2 divided by m1 plus m2 multiplied by v square. What is v, students? V is the initial relative speed with which the blocks were moving. So this is the, and you can see the spring is in unnatural length, right? So there is no compression or elongation in the spring at t is equals to 0. So what can I say now, Sergi? I can simply say that the total initial energy that the system was having must be equal to the total final energy. So all I have to do is equate the total and the final, initial and the final energies, and that's it. So the initial kinetic energy half mu times of v squared. What is v, students? V is the relative speed with respect to origin, or relative speed with respect to the first mass, that's 0, must be equals to half times of mu times of now relative speed Vr at any random time t whole square is going to be plus half times of k times of x square. This is the total energy equation that I have. So Sergi, if I have two different blocks and I give impulse to one of them, that means I gave the energy in form of kinetic energy. So that kinetic energy is gonna oscillate between kinetic energy to potential energy, potential to kinetic, kinetic to potential. I hope you are getting till this point, right? So now students, now that we have the formula, I think we can go for a general question. Okay, so imagine I had a block of mass m. Let's just change the values of that. Okay, what should I take the value? Random values, 10 kgs. I have a block of mass 10 kg. I am attaching with a spring. Let's say the spring constant now is going to be 100 Newton per meter, students. And I'm connecting this whole mass with another 20 kg block. Let's say initially at t is equals to 0, I gave it a speed of 10 meter per second. So as we all know that the speed of the 20 kg block is going to decrease and the speed of this 10 kg block is going to be increased. So students, I am telling a general scenario in which, let's say, the speed of this 20 kg block has been reduced to 8 meter per second. So this is the speed of this 20 kg block. The two questions that I have right now is I first have to find the speed of the 10 kg block and I also have to find the compression in the spring. Are you getting till this point? Perfect. So Sergi, I just have to calculate the compression in the spring and final speed of the block. So for the final speed of the block, I should just use the conservation of momentum. Okay, so initial momentum was around 160. That must be, sorry, it was 200, right? So initial speed was 200. So initial momentum of the whole system, it was going to be 200. That is equals to the final momentum of both the blocks. So it's going to be 160 plus 10 times V, where V is the final speed of the 10 kg block. So from this conclusion, I can simply say that the final speed of this 10 kg block is going to be 4 meter per second. What about the compression in the spring, Sergi? Definitely you got the formula beta. What the formula says, half times of mu times of V relative at t is equals to 0 whole square is going to be half times of mu times of V relative at any general point, right? Adds a function of time whole square plus half times of k times of x squared, where k is the spring constant, right? Now you just have to substitute the values, right? So you just are going to be taking, okay, first of all, we'll just cancel out half from each side. I'll simply say mu times V squared. So mu is the value 200 divided by 30. So it's just going to be 20 divided by 3 times the relative velocity in the initial state. That's 100. Must be equals to again 20 by 3 multiplied by, now since we're getting the value of the final speed of the 10 kg block is coming out to be 4 meter per second, the relative velocities between them will be 4, so it's going to be 16 plus half times of the, sorry, anyhow the half has been cancelled, right? So it's going to be 100 times of x squared. So what I'm left with is, the students, I'm left with this value now. So 20 by 3 multiplied by 100 minus 16 is going to be 84 divided by 100. So whole multiplied by 1 upon 100 is the value of x squared, and you can calculate from this whole expression. It's going to be, I think so, 1680 divided by 300 is going to be x squared. So the value of x is going to be root of all that. So this is the max, this is the compression at this instance. So that was the question, students, one of the very classical questions in physics. Now the next thought we could apply to this is, how would the things go if I place this whole assembly on a rough surface? So that remains a mystery for the next class, students. Thank you so much.